Now in this session, I will explain low pass filter. This is the third concept. Third concept here is constant K low pass filter. A T or pi type of filters or networks can be called as constant K filters if Z1 and Z2 are opposite type of reactances and they satisfied the relation Z1 Z2 is equal to K square, where K is nominal impedance or design impedance. Let me explain once again here. A T or pi type networks are said to be constant K filters if Z1 and Z2 are opposite type of reactances and they satisfy the following relation. That is Z1 Z2 is equal to K square, where K is nominal impedance or design impedance. Okay. Whether it may be a constant K low pass filter or constant K high pass filter or band pass filter or band stop filter, the main things that we are going to study here are: one is first one is this one, nominal impedance, calculation of nominal impedance. K, it is normally represented with K. Second one is cutoff frequency. Third one is attenuation constant. Cutoff frequency is normally represented with Fc, as I already explained. Attenuation constant is represented with alpha. Fourth one is phase constant beta. And fifth one is characteristic impedance. Sixth one is designing the filter or design of filter. So these are the concepts that I am going to explain in any filter, any type of filters. Okay. So first, before going to explain or calculate this nominal impedance, first let me draw the T and pi type of networks. The reason behind the drawing the T and pi type of networks here are to calculate these nominal impedance, cutoff frequencies, attenuation constant, all these things. So first, T type of network. T type network. As we already discussed this T type of network, it is having the impedance of Z1 by 2. It is also Z1 by 2. It is Z2. Right. So for this constant K type of filter, these Z1 and Z2 both are opposite type of reactances. It is 1, 1 dash, 2 and 2 dash. Next for pi type of network. For pi type network, it is pi type network. One dash, 2 dash, and it is normally represented with 2Z2. It is 2Z2. It is Z1. Okay. Now I need to calculate this nominal impedance. So in case of low pass filter, the series branches are inductors and the shunt branches are capacitors. That we need to know. That is Z1 is equal to J omega L. This is series branches are inductances and shunt branches are capacitors. Yes, capacitors. Z2 is equal to Z1 is equal to JXL and Z2 is equal to minus JXC, that is equal to minus J divided by omega C. Okay. Now here, if Z1 is inductance and Z2 is capacitance, then this filter is said to be low pass filter. So for low pass filter, let me draw this. Here it is Z1 is equal to J omega L. Then what is Z1 by 2? It is Z1 by 2 is equal to J omega L by 2. Next, 2Z2 is equal to it is minus 2J into 2J by omega C. I can write it as minus J divided by omega C by 2. So what I mean to say here is, if the impedance is half, inductance will become half. If the impedance is double, then the capacitance will become half. That we have to understand here. So now let me draw these T type of networks and pi type of networks, replacing these impedances with inductances and capacitances. So for low pass filter, this Z1 by 2, it is an inductance. This Z1 by 2, it is also an inductance. This Z2 is a capacitance. It is 2 dash. It is 1 dash. And it is Z1 by 2. This is Z1 by 2 here. That is equal to, it is L by 2. Here also it is Z1 by 2. It is L by 2. It is Z2. So it is C, capacitance itself. Now this is for pi type of networks. So for a low pass filter, the series branches are inductors. So it is an inductor. And the shunt type of branches are capacitors. So it is capacitor. Okay. So it is 2 dash. It is 1 dash. and this inductance is only Z1 here, so it is L. This capacitance here, this impedance is doubled, that means this capacitance should be half, it becomes half, it is C by 2. This is the representation of T and pi type of low pass filters. So it is a T type low pass filter, it is pi type low pass filter. Okay, now I need to find all these 6 parameters or 6 parameters. Okay, all the 6 parameters for this T and pi type of constant K low pass filters. First thing here, nominal impedance K. So first thing, nominal impedance, that is 7th page it is, this is 7th one. So nominal impedance, first one, nominal impedance, which is represented with the letter of K. We know that this nominal impedance Z1 Z2 is equal to K square. From this expression we will calculate this nominal impedance for any type of network. Z1 Z2 is equal to K square. So what is Z1? Just now we wrote that Z1 is equal to, it is J omega L. And what is this Z2? Sorry, it is okay, Z1 is equal to J omega L. And what is this Z2 here? It is minus J by omega C, that is equal to K square. This J into J is nothing but J square, that is minus 1. Minus 1 into minus 1 is plus 1. So this omega and this omega will get cancelled here. So L by C. So L by C is equal to K square. So from this, K is equal to square root of L by C. So this is the expression for finding the nominal impedance of a low pass filter. K is equal to square root of L by C. Next thing, cutoff frequency. Second thing here is cutoff frequency. Which is represented with the letter of Fc. Okay, this cutoff frequency, here this cutoff frequencies we can get it from these two expressions, that is Z1 by 4 Z2 is equal to 0 and Z1 by 4 Z2 is equal to minus 1. So if I make Z1 by 4 Z2 is equal to 0, what will become? We will calculate here. Z1 by 4 Z2 is equal to 0 means Z1 is equal to 0. Z1 is equal to 0 means Z1 is J omega L. J omega L is equal to 0. From this, omega is equal to 0. That means F is equal to 0. Means it allows the frequency starting from F is equal to 0. This expression will give the information about the frequencies from which the signal passes, the range. So it allows the frequencies from F is equal to 0. Next, another cutoff frequency here, that is Z1 by 4 Z2 is equal to 0. That is Z1 by 4 Z2 is equal to minus 1. So Z1 is equal to minus 4 Z2. So Z1, what is Z1 here? J omega L. Z1 here it is J omega L. That is equal to Z2. Minus 4 into Z2 here is minus J divided by omega C. Now this minus and minus will get cancelled. J square is equal to, what is this? It is minus, it is J square, it is J and this j will get cancelled. So minus 1 minus 1, it is into minus 1 is plus 1. So omega, if I cross multiply it, omega square LC is equal to 4. Now omega square is equal to 4 by LC. Now omega is equal to 2 by root LC. So this is nothing but the cutoff frequency, omega c, 2 by root LC. Or this omega is equal to, we know that omega is equal to 2 pi f. In case of normal frequency, it is in hertz, it is in radians per second. It is in radians per second. It is cutoff frequency, so that I have to represent, or I need to provide the subscript as c. It is c here. Now fc is equal to omega c divided by 2 pi. So what is omega c here? 2 by root LC. 2 divided by root LC divided by this 2 pi. So this 2 and this 2 will get cancelled. Finally fc is equal to 1 by pi root LC. So this is the cutoff frequency. So this is the cutoff frequency for a low pass filter expression. Means if it is a it is, as we already discussed, it is a frequency versus amplitude of the signal. The strength of the signal is maximum from 0 to fc. So these are the cutoff frequencies. 0 is one cutoff frequency, it is fc is another cutoff frequency. Using these two expressions, we will get this cutoff frequencies, right? This is nothing but passband, as we already discussed in last class. Next, third thing here is cutoff frequency is over, and it is a stop band. It is nothing but stop band. It is stop band. Another thing here is attenuation constant alpha. Third one, attenuation constant alpha. Next, so this attenuation constant alpha, I need to use the expression in stop band only. We got the expression for attenuation. So for pass band, the alpha value should be equal to 0, and for stop band, the expression that we already got, the expression for a stop band, this expression is 2 cos h inverse of square root of z1 by 4 z2. So this is the expression. I think we already found this expression in case number 2. So this is that the expression, yeah. For alpha, it is for stop band, alpha is equal to 2 cos h inverse of square root of modulus of z1 by 4 z2. So it is modulus of z1 by 4 z2. So use that expression to find the value of the expression for this alpha. To find this expression for alpha, solve the z1 by 4 z2. What is the value of z1 here? It is, I need to take the modulus also here, modulus of. So it is j omega L. Z1 value, Z1 is, that is a what is that, inductance. So it is j omega L. 4 into Z2 here it is minus j by omega c. Since it is a positive quantity, it is j and j will get cancelled. So it will become omega square L into c divided by 4 here. Means since it is a modulus, even though there is a minus sign, it will become positive. So it is omega square divided by 4 by LC. What is this? Okay, omega divided by 2 divided by LC square, it is omega square. So what is this 2 divided by root LC? It is 2 divided by root LC whole square. 2 divided by root LC is nothing but omega C. So I can write it as omega square divided by omega C square. It is a cutoff frequency. So it is omega divided by omega C whole square. Or I can also write as 2 pi f divided by 2 pi fc whole square. This 2 pi will get cancelled, that is f divided by fc whole square. So this z1 by 4 z2 value is f by fc whole square or omega by omega c whole square, f by fc whole square. If I substitute in this alpha expression, alpha is equal to 2 cos h inverse of square root of this f by fc whole square. This square and this square root will get cancelled. So finally I got it as f by fc. So this is the expression. This is the expression for alpha. It is in stop band, that we need to remember here. In stop band only we will get the expression for alpha. In pass band the value of alpha here is 0. So this is alpha expression in stop band. And let me draw the graph for this attenuation constant by taking the frequency in x-axis and attenuation constant in y-axis. Alpha is equal to, just now we got the expression as alpha is equal to 2 cos h inverse of f by fc. This is the expression. Okay. Now let me draw the graph between alpha versus frequency. This is anyway, it is cutoff frequency. This is the alpha I am taking in y-axis. Now this is for low pass filter. It allows the frequencies from 0 to fc, known as it is pass band, and above the cutoff frequency it attenuates the signals, known as it is stop band. So for it is for pass band. It is for pass band. It is pass band. From where to where? It is pass band, and this is stop band. It is stop band. Okay. So if you use this expression, and this expression is cos h inverse of f by fc. So these type of expressions will give the values like this. Like this. So will give the graph like this. Suppose f is equal to 0, f is equal to fc here. What is f is equal to fc? Suppose f is equal to fc, cos h inverse of 1, I think so it is. So cos h inverse of 1 value is 0, I think so. So it is alpha is equal to 0. It will start from 0. If the frequency increases, f is equal to infinity like that, then this value, finally this cos h inverse of f by fc expression will give the graph like this. So this is the graph between attenuation factor, attenuation constant to the frequency. Next coming to this, what is another thing? That is phase constant, I think. Fourth one is phase constant. Phase constant. It is normally represented with the letter of beta. So you already know that in pass band, in stop band, what is the value of in pass band? In pass band alpha is equal to 0 and beta will have some expression. Let me write here. In pass band alpha is equal to 0, beta will have the expression. What is that beta? So this beta expression, it is 2 sine inverse of square root of z1 by 4z2, this expression. So we already got that expression in case of characteristic of filters. So is it, because it is beta, it is case number 2. Okay, here the expression for beta, just now we derived the expression in last session, that is beta is equal to sine inverse of square root of z1 by 4z2. It is modulus. I need to take the modulus for this. It is in pass band, but it is in stop band. In stop band, so if I got to write that stop band, so here where is the stop band? It is alpha is not equal to 0. Alpha is not equal to 0 means it is the stop band. Means here it is sin beta by 2, cos beta by 2 is equal to 0, means beta by 2 is equal to some pi by 2, sorry, beta by 2 is equal to pi by 2. So what is the value of beta here? Beta is equal to pi. So in stop band, it is in stop band, it is in stop band. So in stop band, beta is equal to pi. Okay, let me write here. In stop band, alpha is not equal to 0, beta is equal to pi. So use these expressions here and draw the graph between beta versus frequency. So the same, it is in beta, I am taking in y-axis, and in x-axis it is frequency. It is a cutoff frequency, it is fc. We know that it is pass band, so this is fc should be, we should write like this. It is pass band, it is stop band, it is stop band. Okay, now if we draw the graph for it, so beta is equal to pi in stop band, so it is beta is equal to pi, so it should be pi. So this is this value, so this value is pi. And in pass band, this beta is having the expression 2 sine inverse of square root of z1 by 4z2. And if you find the value of z1 by 4z2, just now we already calculated this z1 by 4z2, and that value is f by fc. So that is beta is equal to 2 sine inverse of, this value is f by fc. Just now we calculated, because since square root of z1 by 4z2 modulus is equal to f by fc. So this is sine inverse of f by fc expression will follow this type of graphs. So this graph will be like this. Why? Because at f is equal to 0, sine inverse of 0 is 0. It is 0 is the frequency at this. If f is equal to fc, sine inverse of 1 is nothing but pi by 2. Pi by 2, in this pi by 2, 2 will get cancelled, only will get pi here. So in between 0 to fc, this will follows the graph like this. So this is how we need to draw the graph between beta versus frequency. Next, fifth thing here is characteristic impedance. Fifth one is characteristic impedance, which is normally represented with Z0. So this characteristic impedance for T network is square root of Z1 square by 4 plus Z1 Z2. You know that formula. For T network, Z0 T is equal to square root of Z1 square by 4 plus Z1 Z2. If I take Z1 Z2 as a common here, it is Z1 Z2 in the square root. It will become Z1 by 4 Z2. I need to get this type of form here, so I am taking this Z1 Z2 as a common plus 1 here. Now it is Z0 T is equal to square root of what is Z1 Z2? It is K square, and it is 1 Z1 by 4 Z2. There is no modulus here. If there is a modulus, then that is F by Fc, but there is no modulus. If you calculate it, that is here by Z1 by Z2, Z1 by 4 Z2, it is minus because otherwise let me calculate here. Z1 by 4 Z2, Z1 by 4 Z2 is equal to Z1 is j omega L and 4 into Z2 is minus j by omega C. That is equal to j will get cancelled here. It is omega square, so it is minus omega square LC by 4. It is minus omega square divided by 4 by LC. That is equal to minus omega square divided by 2 divided by root LC whole square. That is equal to minus omega square divided by omega C whole square. That is equal to minus omega by omega C whole square. That is equal to minus F by Fc whole square. So finally what I want to prove here is Z1 by 4 Z2 value is minus F by Fc whole square. But here in this case it is a modulus, so that here I am not considering the modulus here. So I need to substitute Z1 by 4 Z2 replace with minus F by Fc whole square. Right. So this Z0 T is equal to K into square root of 1 minus F divided by Fc whole square, and Z0 T is equal to K into square root of 1 minus F divided by Fc whole square. So keep it in a box. It is the characteristic impedance for a T type of network. Next, for pi network, what is that characteristic impedance? Let me find here. Z0 pi is equal to, you know that it is the expression Z1 Z2 by Z0 T. Z1 Z2, we already know that it is K square divided by Z0 T. Just now we calculated as 1 minus F divided by Fc whole square. This K and this square will get cancelled. So it is Z0 pi is equal to K divided by square root of 1 minus F divided by Fc whole square. So this is the expression for Z0 pi, characteristic impedance of a pi network. If you draw the graph between this frequency versus the characteristic impedance Z0, both for it is 0 frequency, it is Fc cutoff frequency, both for T network and pi network. It is pass band, you know that it is pass band, and it is stop band. Okay, so if you draw the graph between this characteristic impedance and the frequency, then if Z0 if F is equal to 0, if I substitute F is equal to 0 in this Z0 T, it is 0, so it is 1, square root of 1 is 1, that is K. So that means for frequency F is equal to 0, Z0 T will have the value of K. What about this Z0 pi? It is also same as that of this one, K only, because if F is equal to 0, this term will become 0, 1 minus 0 is 1, square root of 1 is 1, K divided by 1 is K. So Z0 t and Z0 pi will start from k for a frequency of f is equal to 0. Next, if f is equal to infinity, if f tends to infinity, what is Z0 t? If f is equal to fc, it is the frequency at f is equal to fc. For f is equal to fc, what is the value of f is equal to fc? It is fc. So it is cancelled, will get cancelled. 1, it will become 1. 1 minus 1 is 0. So Z0 t will become 0. So it is f is equal to fc. This point for Z0 t is this one. And what about this one? Z0 pi. F is equal to fc. This is 1. 1 minus 1 is 0. K divided by 0. Anything divided by 0 is infinity. So Z0 pi will be at infinity. So if you draw the graph between for the Z0 t and Z0 pi, these graphs will follow the waveforms like this. This is Z0 t. It is Z0 t, and this is Z0 pi. This is Z0 pi, and this is the value of k. Both will start from k only, right? So this is about the graph between Z0 versus frequency f. Next thing here is, it is 7th to 8th, so it is 8th page. Next 9th page. Next thing here is design of a filter, design of low pass filter. That is 6th one. Design of filter, design of a filter. So this is very, very important. The problems will come from this concept only, design of a filter, okay. So he will give the value of k and cutoff frequency, and he is asked to design the T and pi type of low pass filters. So we know that that means he will give the value of k. What is that k? Nominal impedance or design impedance. And also he will give the value of the cutoff frequency fc, and he is asked to design T type of low pass filter and pi type of low pass filter. So how to design it? Let me explain. So we know that k is equal to square root of L by C. This is the formula for a low pass filter. It is the design impedance or nominal impedance. And also the cutoff frequency for low pass filter is 1 by pi root LC. These formulas we need to remember. Next, so if I multiply with k with fc, then what is this? K into fc is equal to the square root of L by C into 1 by pi into square root of LC. This square root L and this square root L will get cancelled. Square root of C into square root of C is 1 by pi into C. And the value of C here is, if I write a C pi, okay, from this C, the value of C here is 1 by pi into K into Fc. So this is the capacitance value in case of low pass filter. Next, I need to find the value of L here. It is multiplying. Now divide this K divided by Fc. That is square root of L by C divided by 1 by pi root LC. Now this is equal to square root of L by C into pi root LC. I can write like this. So this square root C, this square root C will get cancelled here. So what we got here is pi into L. So it is K divided by Fc. Now L is equal to K divided by pi into Fc. So this is the value of L that I need to place in T and pi networks. So what is a T type of network? We already drawn that. In T type of network, it is a T type of network. So this is the value of L by 2. It is the value of L by 2. It is a capacitance C. It is 1, 1 dash, 2, 2 dash. It is T type low pass filter. And this one, it is pi type. It is pi type. And the values of this one, here it is 2 into Z2. So if the impedance is multiplied with 2, it will be, the capacitance will become C by 2. And if there is an inductor, then that will become 2 times. So it is Z1 only, so it is L, it is C by 2. So it is pi type low pass filter. Pi type low pass filter. So that is about the complete information about this low pass filter, constant K low pass filter. Right. So next session I will explain this high pass filter, constant K high pass filter.